Thank you, Daniele, and it's a pleasure to be here to give a contribution to this workshop. So, let me start with a premise. So, if we have a given optimization problem and a quantum machine is available, and we want to use that quantum machine to solve our optimization problem, we need to represent the given problem in the quantum hardware. However, this representation, the encoding of a given problem into the quantum hardware in general could be very expensive from the computational viewpoint. So the risk is that too expensive classical preprocessing makes unuseful the quantum advantage of our quantum hardware. So if we have in this situation, we can adopt this strategy, the so-called hybrid approach, quantum classical hybrid approach. So we can conceive repeated calls of the quantum hardware into a classical iterative structure to represent optimization problem into the quantum hardware. But the important point is exploiting the quantum resource itself. So the classical part of an hybrid architecture is to enhance the contribution of the quantum part. It's not just a classical help close to the quantum machine. So this talk is mainly focused on quantum annealing. So of course, it's well known what a quantum annealer is. For me, it's a quantum hardware given whose architecture is a spin network where the qubits are placed in the vertices of a graph, like this, for example. This is the well-known chimera topology of DD-wave machine. So, of course, there is also the more recent one. And the edges of the graph represent the coupling between neighbors. So this graph like this is far from to be complete. And this little connectivity could be a problem for the representation of a given problem into the quantum hardware, of course. So, the annealing process is the evolution of this spin network as a quantum system toward the ground state of an Ising Hamiltonian. So, a quantum annealer solves this optimization problem, this general optimization problem. So, at least in an ideal case, a quantum annealer finds the global minimum of this function energy, that is the spectrum of the Ising Hamiltonian, in constant time. For the D-wave 2Q is 20 microseconds, of course. So the initialization of an annealer is twofold. We have we need the assignment of the weights that are the coefficients of the Hamiltonian and the energy function, and we have to map the binary variables of a given binary optimization problem to the physical qubits of the quantum hardware. From my viewpoint, the main limitation of a quantum annealer is the few connectivity of the little connectivity of its architecture. And we have at least 3 possible solutions to manage this issue. So the improvement of the hardware, of course. If we have a complete graph, we can directly map a QBO problem into the quantum hardware, of course. We can use and apply classical combinatorial calculus to formulate efficient classical preprocessing to represent the problem into the quantum hardware. Or then this is our strategy is the formulation of hybrid quantum classical algorithms. So this is a picture showing the general hybrid paradigm of quantum computing, where the quantum hardware is embedded in a classical iterative structure in order to improve the performance of the quantum hardware itself. This is our approach starts from the idea of taboo search. Taboo search is well known in classical computer science. It's a kind of local search where you explore the solution space. The worsening solutions have non-zero probability to be accepted. And the important part of the taboo search is the penalties, the penalizations on the already visited solution to avoid a redundant search in the solution space. So the idea is, we try to implement the taboo search paradigm into the quantum annealer. So we consider a quantum annealer, and we can use it to generate candidate solutions of an optimization problem, such that the quantum states corresponding to the already visited solutions are penalized. Penalized, when I say penalized for a quantum state, I mean that a quantum state is far from the ground state where the solution of the problem is encoded. Okay, so a taboo search in terms of a quantum annealing, we have an energetic penalization of the set of quantum states corresponding to the set of solutions. So this is a good choice, for example. If we choose these weights for an Hamiltonian of a quantum annealer, the spin glass under the architecture of a quantum annealer, we can penalize a class, a set of solutions represented by the quantum states, quantum eigenstates of the Hamiltonians before. So we can define this classical object that we call taboo matrix in this sense. So this is nothing but the matrix with these weights as elements. So in general, a taboo implementing encoding of a binary optimization problem is the general encoding of an optimization problem given by a binary optimization objective function f. So the taboo implementing encoding has this general form. Mu is the encoding of the objective function f into the annealer architecture. So we have E, the energy function of the quantum architecture. We have the weights matrix reproducing some properties of the objective function. So we have the weights where the objective function is partially represented. We have the additive action of the S matrix to penalize the already visited solution in the spirit of taboo matrix, and the permutation describes the mapping of the binary variable solved problem into the physical qubits. And we have the Hadamard product, so the product between matrices element per element, element by element, to reproduce the information of the topology, so the connectivity of the graph. Okay, so our technique is called quantum annealing learning search, because we have a taboo search in the sense that I just explained in the solution space, but we have a guided evolution in the space of encodings toward a faithful representation of a given problem into the hardware architecture. So we have do parallel search in these two spaces. So the hybrid scheme can be summarized in this scheme. The hybrid scheme can be summarized in this form. So we have to define a sequence of taboo implementing encoding mu such that this requirement is satisfied. So of course we have the taboo search requirement, so already with the solution penalized, energetically penalized in sensor quantum states. We need the improvement of representation of the objective function into the architecture, the quantum architecture. And of course we require that the sequence of encodings converge to a faithful encoding. So we have to end our search with a limit encoding that is faithful. So in the architecture, we have the precise, the good, the best representation of the objective function. And this hybrid scheme is realized by repetitions of the calls of a quantum machine to an iterative structure. So let me show you the pseudocode of a simplified version of our hybrid algorithms. So initially, two solutions are randomly generated, and the red lines are the calls to the quantum machines. And the best solution is used to initialize the element Z star and the best encoding mu star, and the other one is used to initialize the taboo matrix. So in the iterative part, candidate solutions are repeatedly generated and tested. So the good solution is used to initialize the best encoding so far, and from the best encoding so far, by deformation, we generate a next encoding, and we produce, in this sense, our sequence of encodings. And the discarded solution are used to update the taboo matrix. Okay. So if we consider a quadratic ecostate binary optimization problem, a QBO problem, like this, we have results about the asymptotic convergence of the hybrid algorithm. In particular, we can describe this quantum classical search based on a quantum annealing as an inhomogeneous Markov chain with nice properties. And so we have a limit distribution that is non-zero only on the solution on the solutions of the considered optimization problem. So in this sense, the hybrid search converges asymptotically to the solution of the problem. So now this is a preprint, and you can find it on archives, and it's an extension of the learning search with a quantum annealer, and we consider an adiabatic quantum computer. It's an universal computer in general, because AQC is a universal model for quantum computation, and the goal of the adiabatic quantum computing learning search is, given an optimization problem, we want a hybrid procedure to find an adiabatic quantum algorithm to efficiently solve it. So we propose in this work, in this paper, an hybrid algorithm like that is a generalization of the algorithm that I summarized in this talk, where a convergent taboo-inspired search finds an encoding of a given problem into an adiabatic quantum architecture, providing an adiabatic quantum algorithm and its runtime. So the idea is use an algorithm like this as a source of examples. So given a class of optimization problems, we have a procedure to generate quantum algorithms to solve that problems. So the idea is take this source of examples and apply classical technique of machine learning to learn new quantum algorithms. So let me tell you something about the work in progress. And the most urgent question that we are writing the code for the implementation of the quantum annealing learning search into the D-Wave real machine with the collaboration of the German Aerospace Agency, and the application of the main idea of our learning search, quantum annealing learning search, to represent that efficiently data into quantumizing model. So because the same technique to implement a taboo search can be adapted to an efficient representation of large amount of classical data into quantum hardware if your hardware is an Ising model. And that representation is crucial for data compression, of course, and machine learning. So we plan to apply this viewpoint to quantum data compression and quantum machine learning. And another goal, and we are working on it, is a formulation of this learning search beyond optimization problems. So, for example, in an ideal scenario, given a class of problems, we need a procedure based on these notions that I try to explain today, in short. A procedure given a class of problems, a procedure to learn quantum circuits, for example, to solve that problems. So in this sense, I think this road could lead to in the direction of quantum compilers. So that's it. Thank you for your attention.